Our speaker today is Prateek Kumar Viswakarma, and he will speak on inequalities for totally non-negative matrices. Prateek, the floor is yours.
Thank you so much. First of all, let me begin with thanking Professor Sandra Kingen for giving me the opportunity to be here and speak with you all. Just to give you all a brief introduction about myself, I graduated just last year, February, from the Indian Institute of Science. And since then, I've been working here at the University of Regina as a PIMS postdoc. In this talk, we will talk about inequalities for totally non-negative matrices. So let's begin with some prerequisites and definitions. So a real matrix is called totally non-negative, Tn, if all of its minors or the determinant of all of its submatrices is non-negative. So which means we would want to check if all the 1 by 1 minors, which are all the entries of the matrices, all the 2 by 2 minors, all the 3 by 3, 4 by 4, and so on, which could be any principal, non-principal, contiguous, non-contiguous, all of the minors are required to be non-negative. So for example, the zero matrix obviously is totally non-negative. The matrix with all entries 1 is also totally non-negative. The identity matrix is also totally non-negative. This 2 by 3 matrix over here is also totally non-negative because all of the entries are non-negative, and all the 2 by 2 minors, the 3 2 by 2 minors in this matrix are also totally non-negative. The next matrix, which is the 3 by 3 real matrix here, is also totally non-negative because all the 1 by 1 minors, which are all the entries, are non-negative. The 2 by 2 minors are also non-negative. The determinant of the matrix, which is the 3 by 3 minor here, is also non-negative. Therefore, the matrix is totally non-negative. However, the last matrix, the last 3 by 3 matrix over here, is not totally non-negative, because if you look at the top right corner 2 by 2 matrix here, this determinant is 2 minus 6, which is minus 4, which is not non-negative. Therefore, this matrix, this 3 by 3 matrix, is not totally non-negative. For more interesting examples, if you make a matrix in which the ijth entry is the minimum of ij, then that matrix is also totally non-negative. In fact, if that matrix is square, then that matrix happens to be non-singular. For a matrix which has appeared in analysis or in several important proofs regarding total non-negativity is the generalized Van Braun matrix. So you construct this matrix by picking non-negative real numbers x1, x2, xm, and any real set of real numbers alpha 1, alpha 2, alpha n. Each of them are pairwise distinct. And then you construct the matrix xj to the power alpha I like this. Now this matrix is totally non-negative. In fact, the determinant of this matrix, whenever it is square, is positive, and therefore the matrix is in fact invertible as well. So for further more interesting examples, suppose we need to consider a directed acyclic planar network on which the edges have non-negative weights. So suppose we have a directed acyclic planar network like this. So on the left side, we have vertices in which the in degree is 0. So which means these vertices are our source vertices. And suppose the vertices on the right hand side, on the extreme right side, have out degree 0. So suppose these are our sink vertices. So so we have a planar network kind of thing here. I mean, directed acyclic planar network, in which all the edges have non-negative weights. And suppose for this planar network P, we construct a matrix AP in which the ijth entry, to write down the ijth entry, we simply look at all the paths starting from vertex I on the source side to starting from vertex I on the left side and ending at vertex J on the right side. So we identify all the paths starting from I and ending at J, and then we simply add the weight over the collection of all those paths. So if ijth entry is aij like this, then the matrix then there is a natural way. So if matrix AP corresponding to the planar network is constructed using this formula, then because of the structure of the planar network, which is that it is directed acyclic planar network, there is a natural way, there is a natural formula to compute the minors of this matrix AP as well, in terms of the sum over all families of disjoint paths P which start from set of vertices I and end at set of vertices J. If so, this computation will give us the minor of matrix AP corresponding to row indices I and column indices J. Now, because the weights in the planar network are non-negative, this clearly implies that the minors of AP are non-negative, and therefore the matrix AP is totally non-negative. Now, the converse of this statement is also true, which is, so what would be the converse? So what we just saw is that if we have a planar network with non-negative weights, then we can, whenever we construct a matrix AP like this, then AP is totally non-negative. The converse of this statement would be, suppose I'm given a totally non-negative matrix. Is there any way that I can construct a planar network with non-negative weights for which the matrix AP would be the same as the matrix that I was given? So the converse is true, and to see the converse, before we see that, let's look at a example first. So suppose we have a planar network starting from vertices 1, 2, 3 here and ending at source sink vertices 1, 2, 3 like this, and the weights of each of the directed edges are given like this. Then we construct the matrix, the 3 by 3 matrix like this. So to write down the entry A11, we simply look at all the paths starting at vertex 1 and ending at vertex 1. And for this planar network, there is only one way to do that. It is to just simply go straight across using edges with weights 1 and 2. So therefore, A11 is simply 1 times 2. To write down the entry A12, we simply have to look at all the paths starting at 1 and ending at 2. And we simply write down the weight of that path. The weight of that path is 1 times 5. So that's 1 times 5. And to write down A13, we'll look at all the paths starting from 1 and ending at 3. In this planar network, there are no such paths, so that weight is overall 0. For A21, we look at all the paths starting at 2 and ending at 1. And there is only one way to do that, and that is by using the edge with weight 4 and edge with weight 2. So overall weight of this path is 4 times 2. So that's what we write there. And there are no other ways to write down. And next is to write down, if we try to write down A22, then we have to look at all the paths starting from 2 here and ending at 2 here. And there are two ways to do that, which is, first one is to just simply go straight across like this using path 3 times 2. So we write 3 times 2, plus there is another way, which is by using path 4 times 5. So we just simply add that value to compute A22. And we keep on, and we simply keep doing the same thing until we draw the matrix completely. So the matrix is this corresponding to this given planar network. Now suppose we want to compute the minor of this matrix corresponding to row indices 1, 3 and 2, 3. Then we simply look at all the paths starting from vertices A, all the disjoint families of paths starting from vertices 1, 3 on the left side and ending at vertices 2, 3 on the right side. So one way to do that is by going from 1 to 2 using 1 times 5 and going from 3 to 3 using 5 times 2. So the overall weight would be the product of all of these weights, which is 1 times 5 times 5 times 2. And then we add what is another way to traverse this traverse from 1 3 to 2 3. And another way is, again, we use 1 times 5 to go from 1 to 2, and we use 4 times 7 to go straight across from 3 to 3, and the overall weight of this path, these set of paths, is 190. It is also equal to the determinant of the matrix submatrix corresponding to rows 1, 3 and columns 2, 3. So 5, 0 and 10, 38. And just to show you one more example, suppose we want to compute the determinant of the matrix. So determinant of the matrix A corresponds to rows 1, 2, 3 and columns 1, 2, 3. So we, in the planar network, we simply have to identify all the families of disjoint paths starting from 1, 2, 3 and ending at 1, 2, 3. And there is only one way to do that, in which you go from 1 to 1 straight, you go from 2 to 2 straight, and you go from 3 to 3 straight. And the overall weight of this family of path is just the product of 1, 2, 3, 2, and 4, 7, which is, and 336 is the value, which is the determinant of the matrix. So that's one of the examples to describe what we just saw previously. And to now, let's come back to looking at, to seeing how we can see the converse of the previous lemma that we saw. To see the converse, suppose EUV is the elementary matrix in which the UVth entry is 1 and rest of the entries are 0. Then it was proved by Whitney that if you pick any square non-singular totally non-negative matrix, then that totally non-negative matrix can be factorized into products of elementary matrices of the form identity plus W EUV. So where W can be any positive real number and U and V are consecutive integers. So they have to be either 1, 2, 2, 3 or 3, 2, something like that. So the matrix can be factorized into products of matrices like this and a diagonal matrix with positive diagonal entries. More precisely, the factorization can be written in terms of factors which look like this, or which appear in this specific order. So this factorization that is written here does not commute. So for instance, we need to start with j is equal to 1 and then k is equal to n minus 1 and then go up to j and then write the factors in this order of appearance of j and k. So now, using this factorization, how do we draw the planar network corresponding to any matrix A, any invertible P in matrix A? So what we do is we simply draw the. So now look, if you look here, these elementary factors, these identity plus some non-negative real number and then elementary matrix EUV, the planar network corresponding to these factors is not very difficult to draw. And once we know how to draw the planar network corresponding to each of these factors, we will, using Cauchy-Binet formula, it's not very difficult to, we can draw the planar network corresponding to A. For instance, suppose n is equal to 5, and so suppose we want to draw the planar network for 5 by 5 totally non-negative matrices. Then if we look at this factor, the factor on the extreme left of this factorization is identity plus W times E54. So it will be something like this, right? So the factor appearing on extreme left of that factorization is identity plus W E54. So which is a diagonal matrix, except that there is one entry which is the 4th entry, which will be W. Now what is the corresponding planar network? We simply draw a set of source vertices and sink vertices. And because all the diagonal entries are 1, we draw directed edges from 1 to 1, 2 to 2, 3 to 3, and so on. And we give them weights 1 each because the diagonal entries are all 1. Other than these entries, only one entry is non-zero. So we draw a straight edge from 5 to 4 and give that weight W. So this is how we draw the planar network corresponding to a factor like this. Similarly, we can draw the planar network corresponding to any of the factors appearing in this factorization. For instance, if we want similarly, if we want to draw a planar network corresponding to a diagonal matrix with diagonal entries d1, d2, d3, and so on, we simply draw planar network like this, in which we join 1, 1, 2, 2, 3, 3, and the edge weights are given like d1, d2, d3, which are all the diagonal entries of the diagonal matrix D. So once we know how to draw once we know that these are planar networks corresponding to those factors, using Cauchy-Bonnet formula, we can simply concatenate those those planar networks corresponding to those factors to draw the planar network corresponding to matrix A. And that is how we can say that the converse of this statement is also true. So for instance, if you concatenate all the factors for 5 by 5 PN matrices, then the planar network that you would get after removing all the redundant vertices and edges would look like this. So in which all the edges are directed from left to right, and the weights of all the horizontal edges is 1 except for the edges D1, D2, D3, and so on. And the non-horizontal edges could have any non-negative weight. So this obviously corresponds to, as we discussed, only corresponds to invertible PN matrices, but similar results are true. I mean, same result is true for any totally non-negative matrix, except that you may have 0 entries here and there. But for our purposes, because we simply want to discuss determinantal inequality, because of continuity, it is enough to work with invertible PN matrices. And to summarize this preliminary discussion, for n by n PN matrices, the planar network would look something like this. Now, we have seen. Oh, before we continue, let me introduce some notations. So, for instance, we will use box mn to denote all the set of integers from m through n. We will use box n to denote all the integers from 1 through n whenever n is more than 1. For matrix A and subsets S and T of box n, we will use S complement to denote the complement of S. We will use A subscript jk to denote the submatrix in which the jth row and kth column is absent. We use AST like this to denote the submatrix with row indices S and T, with row indices S and column indices T. We use AS to denote the principal submatrix corresponding to row S and column S. And we use K plus or minus S to denote the translation of set S according to the sign and according to the translation factor. Now so far, I mean, in our preliminary discussion, we saw that totally non-negative matrices are essentially certain combinatorial objects because they correspond to sums over families, because the minors of these matrices correspond to sums over families of disjoint paths. And this observation, this result is obviously very useful in comparing minors. Now, comparing minors is not a very difficult question here because of the result due to Whitney and Lindstrom-Gassoveno. It's not very difficult to see that you can compare two minors overall totally non-negative matrices if and only if those minors are exactly equal. However, things become more complicated if you want to compare two products of minors, for instance. So suppose you want to compare products of minors like this. So you want to multiply two minors like these, and you want to see when they are comparable over all totally non-negative matrices. It turns out that understanding about planar networks is not sufficient to really go about this, to really understand when we can compare two products of minors, because we will have to deal with paths, which families of paths in which there is overlap. Those paths are not necessarily disjoint anymore when we multiply minors like this. And of course, there is a lot that we can say using just the understanding of planar networks, and we will see in this talk itself what all we can discuss about. But if you want to really learn about what is the relation between products of two minors of totally non-negative matrices, then we will have to look at certain eminence which were discussed in the very, very beautiful work of Rhoades and Skandera. But this specific work is not in the scope of this talk. But I just thought to put the references for the audience. Now the end goal.
Can I ask a question?
Yeah.
Do you have a quick description of what an imminent is, or is that outside the scope of the talk?
No. So imminent is like, so you have you do Laplace expansion of determinant. So you have sum over sine of sigma times you multiply all that. So you replace that sine of sigma scalar with something else, some other function. And that's a general a general definition of an eminent. Yeah, so that's how. Now, what do we so what is a general aspiration? I mean, as far as I understand, because of the way people have been working, going about the total non-negativity, is that we want to understand what happens. So we know what is a determinant, we know what is a product of two determinants. So natural question is, what would be the product of three minors like this? Well, like, so we have a description that if you multiply two minors, we have a description in terms of in terms of eminence. But it's not very we don't really know what would happen if what is the description of products of three minors. And just last week I was at University of Pennsylvania and I was giving the same talk, and Rhoades Skandera was there in the talk, and as an audience, and I asked him directly whether they are working in describing products of three minors like this. And so far, I got the answer that he doesn't know if there is anyone who is working in this direction. So that's one of the open questions that we would want to really get some answer, so that we can compare, for instance, products of three minors like this. So that's the general aspiration that everyone who is working in total non-negativity have. But in this talk we will focus on something that we can answer. For instance, if we simply recall that totally non-negative matrices are those real matrices which satisfy certain determinantal conditions. In other words, these are those real matrices which satisfy certain determinantal inequalities. So because of this reason itself, seeking determinantal inequalities or looking for all the determinantal inequalities satisfied by these totally non-negative matrices is sort of natural. So for instance, so why this question, why this specific question is a special case of the aspiration that I discussed before, because once we understand what these multiplied minors are, we would know how to answer the related questions related with determinantal inequalities, because those are simply comparisons between minors, or comparison between sums of products of minors with zero. So we are in a way dealing here in this talk with a simpler question. Simpler or simplified version of the same question. So one of the classical example of determinantal inequality is the Hadamard inequality, which says that if you multiply all the diagonal entries of any totally non-negative matrix, then that product is always going to be more than the determinant of the matrix. Now, combinatorially, we can see this in the following way. So, determinant of the matrix A corresponds to all the paths starting from vertices 1 to n. Not all the paths, sorry. All the disjoint paths starting from vertices 1 through n and ending at vertices 1 through n. So, the right-hand side of this inequality corresponds to disjoint paths from 1 to n to 1 through n. However, the left-hand side of the inequality, so for instance, A11 corresponds to all the paths starting at 1 and ending at 1. A22 corresponds to all the paths starting at 2 and ending at 2, and so on. So when we multiply these paths like this, we simply multiply or take account of all the paths from 1 through n to 1 through n. So this clearly means that paths sitting on the right-hand side of this inequality are included in the set of paths on the left-hand side. So therefore, we have the Hadamard inequality, and that's the combinatorial interpretation. So, however, and to see another intriguing example of such determinantal inequalities, consider 4x4 totally non-negative matrices A and expand its determinant along the first row. So we will have something like determinant A equals A11 times determinant A11 minus A12, and so on. Now this is a determinantal identity, Laplace determinant identity. And because A is a totally non-negative matrix, which means the last entry in this expansion, which is which is A14 determinant A14, is going to be a non-negative real number. So it is obviously obvious that if we drop the last term from this identity, we should be getting a determinantal inequality of this form, right? Now, it is not very straightforward to see that if we drop the last term now, which is again a non-negative real number, A13 determinant A13, we again get a determinantal inequality for all totally non-negative matrices A. However, the sign of the determinantal inequality changes. And if we continue doing the same process again, that is, if we drop the last term again from the inequality, then we get a determinantal inequality which holds true. However, again, the sign of the inequality changes, and that inequality is the well-known Fisher's inequality. So in this example, we saw that there is a way to extract determinantal inequalities from determinant identities, determinantal inequalities for totally non-negative matrices from determinantal identities which hold for all real matrices. Now, there is, and we have been able to, we will see in detail what more we can do with this kind of with this kind of beginning. For instance, we have also been able to extract determinantal inequalities in the similar way from generalized Laplace identity. For instance, these two inequalities hold for all totally non-negative matrices. For all, 4x4 totally non-negative matrices, if we choose our row indices P and Q like this, and we will see this inequality in a bit more detail later. And we have also, so in addition to seeing how we can extract inequalities from known identities, we have been able to devise a rule or a method or an algorithm, if you will, to obtain inequalities, novel determinantal inequalities from known determinantal inequalities for totally non-negative matrices. For instance, these two inequalities at the top hold for P and Q, holds for row indices P and Q, these values of P and Q. However, there is a nice way to explain that these two inequalities also hold for values P prime and Q prime. And there is a nice way to explain why that's really true. Now, in addition to this introduction of, in addition to this application of the introduction of these index row operations, we have also been able to explain that precisely when determinantal inequalities like these hold true. Now, obviously, as we saw earlier, that these types of determinantal inequalities can be discussed in terms of certain eminence. However, we can also describe these types of inequalities using just the index row operations, index row and index column operations that we will introduce in a bit, which are simply the application of the fundamental theorem due to fundamental factorization theorem due to Whitney, which we saw in the beginning. So yeah. So before we continue, let me just let us quickly see a definition of a determinantal inequality over Tn matrices. So for our usage, we will simply call a real linear combination of certain products of minors, which is non-negative overall totally non-negative matrices, a determinantal inequality for totally non-negative matrices. So yeah, I mean, I've seen that people would want to instead refer to determinantal inequalities as polynomials in minors, which are non-negative polynomials in minors. But for our application or usage, it is better to look at this form of determinantal inequalities. So suppose we have something like that. For instance, we will call a determinantal inequality multiplicative if it compares products of two minors like this. And we call something additive if it basically compares sums of products of minors with zeros for all totally non-negative matrices. Now, as I promised in the beginning that we would discuss how we can extract determinantal inequalities from known identities. So let's start with the classical identity due to Laplace, which basically says that if you take the dot product, or if you take the dot product of ith row of A with the jth column of its adjugate, then whenever I and j are equal, you will get determinant of the matrix, and when they are not equal, you will get 0. Now, looking for the refinement of this Laplace identity for Tn matrices makes sense because of these two classical reasons. One is that, so totally non-negative matrices have variation diminishing property, which basically means that the number of, that if A is a totally non-negative matrix, and if you count the number of sign changes in vector x, and you compare it, then the number of sign changes in vector x is always more than the number of sign changes in vector ax for all real vector x, for instance. So, and Schoenberg was able to prove this property, and the proof of this, and in the proof of this theorem, it was crucial to understand the relation between the terms appearing in the Laplace determinant expansion. The another result, another classical theorem in which this relation was sort of useful was was in the reduction theorem due to Whitney, which we saw earlier. So because of these two reasons, these two classical reasons, it's sort of natural to look for refinement of these the Laplace identity. Gantmacher Krein took the first step in this refinement, in which he proved, they proved that if you take the partial Laplace expansion along the first row of any totally non-negative matrix A, then depending on the length of that expansion, length of that partial expansion, you will get an inequality which is either greater than the determinant of A or less than the determinant of A. So, and it is, and to see how we can further refine this classical inequality, we observed that it is not really about the comparison of the partial sum on the left side with the determinant. Rather, it is about figuring out where this determinant term fits in with the rest of the expansion. For instance, suppose I want to expand suppose I want to refine this inequality along the second row of any totally non-negative matrix. Then here is what I will have to look at. So I will expand the classical determinant identity, but I'll have to be a little careful. So if I expand along second row, I will look at A21 times determinant A21 minus A22 times determinant A22. Then I bring in the determinant A term when A22 terms appears. And then I will continue taking the sum further. So with this kind of sum, in which the determinant A term gets adjusted with the diagonal entry, we will end up getting an inequality which looks like this or justifies this phenomena. For that, we start looking at this matrix A star, which is simply the entry-wise product of A with the transpose of the adjugate. So we are simply talking about a matrix in which the entries are A11 times determinant A11 minus A21 determinant A21 and so on, right? And then we subtract the determinant term from all the diagonal entries in this entry-wise product. So once we do that, it is not very difficult to see that the Gantmacher Krein inequality above is simply about the partial row sum along the first row of matrix A star, right? And it basically says that if you take the partial row sum, and depending on the length of that partial row sum, you will get an inequality which is either negative or positive, or which holds for all totally non-negative matrices. So now to really see what happens for other partial row sums of A star, we did the computation and we saw that for the rest of the rows as well of A star, depending on the length of that partial row sum, we will get an inequality. We get an inequality which is either negative or positive for all totally non-negative matrices A. And this obviously refines the classical Laplace identity when I was equal to j. That is when on the right hand side we had the determinant of that um, Laplace identity. And to refine it further for all the cases when I is not equal to j, we obtain that if we take the partial sum again for partial dot product of ith row of A and jth column of its adjugate, then again we get an inequality which is either negative or positive. And mind you, for I not equal to j cases, we don't have to worry about the extra determinant term on the right hand side, because the right hand side is already 0. And now, in the interest of time, we won't be able to discuss the proof of these results. However, let me just talk about them anyway. Briefly. So, to prove the first set of inequalities in this theorem, we simply had to first observe that the conjecture or observe the right kind of inequality that was happening there, and after that, we simply had to adapt to the original proof by Gantmacher Krein. Now, in order to prove the inequalities in part 2, something interesting happens because once we introduce these index row and column operations, which we will do in a while, we will be able to see that in inequalities in part 2 can be derived from the inequalities in part 1 using these index row operations. So certainly we can see that there is a hierarchy among inequalities. For instance, here the inequalities in part 2 can be seen as lower than the inequalities in part 1 because they can be derived. And because of this introduction of this hierarchy, we can see we would want to know what is at the top of the hierarchy. So we will see that we don't know yet what is at the top of what is all at the top of the hierarchy, but clearly because of the way these index row operations work, complementary inequalities are certainly at the top of the hierarchy. And incidentally, for this theorem itself, the inequalities in part 1 are complementary inequalities. So what are complementary inequalities? So minors that are multiplied in any inequality, if the row indices happen to be pairwise disjoint and so are the column indices, then we call such an inequality complementary. So in this case, the following is the proof. And now here's the next result. So because we were able to refine classical Laplace identity, and we also know that there is another classical identity due to Karlin, we started looking at that inequality specifically. So this Karlin's identity holds for all real matrices, whatever that is. We don't have to go into the detail, but it certainly looks very different from the Laplace identity. That's number one. Number two is that if we look at the Laplace identity for all I not equal to j cases, then for certain specific choices of row and column indices in Karlin's identity, we get the Laplace identity for all the I not equal to j cases. And because we have been able to define this version of Laplace identity, it is a natural question whether we can do the same for the Karlin's identity. And we were able to work out that instead of taking the complete summation, which is 0 for all real matrices, if we take any partial sum of any given length L, then depending on the length of that partial sum, the inequality that we get is either negative or positive for all totally non-negative matrices for all row and column indices satisfying the Karlin's identity. Now, the proof of this theorem involves a slightly unique way of application of applying Whitney's bidiagonal factorization theorem, which we saw earlier. And this unique way of looking at the proof sort of led us to the introduction of these index row operations, which we will see in a moment. Now, to summarize, in two theorems so far, we have been able to observe a set of determinantal inequalities in which we basically take partial sums along for some given entries, And depending on that partial sum, we get either an inequality which is either positive or negative for all totally non-negative matrices. So we would want to know what is really happening here, and it is natural to look for more inequalities, set of inequalities that are sort of extracted from classical identities, which hold for all real or complex matrices. So we started looking at the generalized Laplace identity, and we were able to work out this inequality. We won't have to go into the details unless we really have to. But so, for instance, let me just say that this set of inequality holds for the choices, the row indices P and row indices Q, if one is the subset of other. So the inequality holds for many choices of P and Q, or the inequality also holds for the case when P and Q are complementary, and they are in turn equal to the set of all integers 1 through D. So all I want to say here is that in order to prove these set of inequalities, we simply used the reparameterization of totally non-negative matrices in terms of the planar network, and we proved the inequality for the cases P is equal to Q complement is equal to 1 through D. And once we proved these set of inequalities, we obtained what we can refer to as the complementary inequalities. And to obtain the rest of the inequalities that we wrote in the previous slide, we simply had to apply all the index row operations, and we basically obtained the closure of this complementary inequality under the index row operation. So so it seems these index row operations are very useful in obtaining novel determinantal. So enough of this teasing. Let me talk about these index row operations now. So unless anyone wants me to pause for any question or any doubt. Okay. So let's recall that a determinantal inequality over totally non-negative matrix is simply a real linear combination of certain products of minors which is non-negative for all totally non-negative matrices. Now suppose we have a determinantal inequality like that, and we want to and these index row operations work for any two consecutive choices, any consecutive row indices U and V. So suppose U and V is given to us, it could be 1 2 2 3 or 3 2 and so on. Then we define these index row operations RUV, which act on the inequality which is given to us in 4 steps, broadly in 4 steps. So in the first step, it changes all the row indices Ij. So let me call these row indices Ij as I. So it changes these row indices I to IUV in the following way. So if I contains U and it does not contain V, then we switch U and V. Otherwise, we don't do anything. So that's step 1. Step 2 is that we keep count of these switchings in each of these terms, in each of these monomials, or in each of these products of minors. So we count the number of times these switchings are happening in each of the multiplied minors. Step 3 would be to identify those multiplied minors in which this switching is happening the maximum number of times. And number 4, we replace the rest of the multiplied minors with zeros. And once we follow these 4 steps, what we will get is again a determinantal inequality which holds for all totally non-negative matrices. So for instance, if it's okay, I don't know if I can, maybe the board will not be visible very well. So okay, let me continue. So let me do a silly example before we continue. So suppose we look at suppose we have the Hadamard inequality over 2 by 2 totally non-negative matrices. So we have A11 times A22 is more than the determinant of the matrix, which corresponds to row indices 1 2 and row column indices 1 2. So if we apply row operation R12 on it, now note that in A11, the row index is the set containing 1, right? And in A22, the row index is set containing 2. And what R12 does is that it changes 1 to 2 because 1 is there, 2 is absent. So it changes 1 from 1 to 2. It does not change 2 at all in the set containing 2 at all because 1 is absent there. 1 is not there, so there is nothing to change. And this set containing 1, 2, which is the row index set in the determinant of A part, does not change again because 1 is there and 2 is there as well. So there is nothing to switch. So this is step 1. Step 2 is that we count the number of switching that is happening in each of the products of minors. So for instance, in A11 times A22, the switching is happening in A11 term, which becomes A21 from A11. So the number of switching here is 1. And here the number of switching is 0 because in this product of minors, there is nothing is being switched. I mean, 1 is not changing to 2. So here the switching is happening 0 times. And now because 1 is more than 2, we replace these products of minors in which there is any fewer number of switching with zeros. And we get something which is trivial, which basically says that if you multiply A21 with A22, you get something which is non-zero, which is obviously true for all totally non-negative matrices. So that's one example to describe how these index row operations work. To look at a slightly more complicated example, so recall that in theorem A part 2, we wanted to prove this inequality, which basically refines the classical Laplace identity for all I not equal to j cases. So to prove that, we simply start with the Gantmacher Krein inequality, which says that if you take the partial Laplace expansion along the first row, then you get something which is either greater than determinant or less than determinant. Now if you apply row operation R12 on this, you change A1k to A2k because the row index 1 changes to row index 2. Determinant capital A1k does not contain row index 1 at all. So that in this part of the minor, there is no switching. So this remains the same. And similarly, the determinant A part does not do any switching because 1 and 2 row indices, both of them are present here. Now, if we count the number of switchings happening, then all of the terms appearing on the left of the inequality, the switching happens exactly once. However, on the right hand side, the switching happens exactly 0 times. So the determinant A part gets replaced with 0, and the rest of the inequality is proved, which is true, which gives us the proof for I is equal to 2 and j is equal to 1 case. And similarly, if we apply the row operation R23, we get an inequality which holds true for I is equal to 3 and j is equal to 1. And similarly, if we keep applying these row operations, we will end up getting inequalities which hold for all I not equal to j cases, and we get the proof for the refinement of Laplace identity for all I not equal to j cases. And finally, to see the proof of that result, so we want to prove that this inequality that we have here holds true for all totally non-negative matrices. So suppose we call this on the left hand side as G. So we have something like this, and we want to show that this is non-negative. So what we do is we start with totally non-negative matrix A, and we multiply the factor identity plus W EUV on the left of it, where W is any positive real number, and U and V are the same consecutive indices corresponding to the row operation RUV. Then using the well-known Cauchy-Binet formula, it's not very difficult to see that the minors of B correspond to the minors of A using these two formulas. Now, if we compute the original inequality that we had at B, then we get a polynomial in which the leading coefficient is this expression that we want to prove is an inequality. Now, because the original inequality is non-negative, which means this polynomial in W has to be non-negative. which means the leading coefficient has to be non-negative. And that's the proof for this for the lemma that we saw earlier. So yeah, so what are the outcomes of the introduction of these row operations? So we were able to see that um, whenever we have an inequality, we can obtain new inequalities using using the application of these row operations. And second is that because the transpose of P n matrices is again totally non-negative, introduction of these row operations naturally gave us column operations, which operate on the column indices in the similar way. So the lemma that we just proved earlier basically says that if we have an inequality, and then we can apply these words of these row and column operations to obtain novel determinantal inequalities like these. The obvious question, or the important question rather, is to prove whether the converse of this statement is also true. So that's question one, that we would want to see whether it's true in general. Second question is about the existence of the complementary inequalities, so which basically says, and I also sort of alluded to in the beginning, that because of that, whenever we have a determinantal inequality, we would want to know whether it comes from certain other complementary inequalities because of okay, so because we were able to introduce these index row and column operations, we saw that there is a certain hierarchy among inequalities, and because of this hierarchy, we would want to know what is at the top of the hierarchy. And because of the way these inequalities, these index row operations work, we were able to see, I mean, it's not very difficult to see that the complementary inequalities are at the top of the hierarchy. So the second question, general question, is that is there any way to figure out that whatever inequality that we have comes from certain complementary inequalities via the action of these index row and column operations? We were able to see that questions to these two, the answer to these two questions was in affirmative for all the inequalities that we have seen so far, for all the additive inequalities that we have seen so far. However, the set of inequalities that we saw earlier is not very large. So because of this reason, we started looking at the multiplicative determinantal inequalities to really test whether the answer to those general questions were really true or interesting. So we started looking at multiplicative inequalities, which basically compares products of minors for all totally non-negative matrices. In particular, if we compare products of two minors, then we will, for the ease of access, we simply call these kind of inequalities as smallest multiplicative inequalities. And the answer to those two previous general questions was in affirmative for these types of smallest multiplicative inequalities because of the following reasons. Now, if you recall that these row operations work only or act only on the row indices of these inequalities, and the column operations act only on the column indices of these determinantal inequalities. And there is no way yet to figure out if there is any connection between these row and column operations. So to really test whether the converse of that lemma is true, we would have to figure out a way to combine the row indices P1 and Q2, or of the row and column indices on the left hand side of this determinantal inequality. And similarly, we would want to figure out if there is any nice way to combine the row and column indices of the minors on the right hand side of this determinantal inequality. Now, this result, due to Skandera and Fallat and everyone, gives us that combination in terms of R1, R2, and K1, K2. And using this combination, we were able to test that the converse to that lemma holds true for the inequalities in part 2. So we basically were able to show that if we have a determinantal inequality of type 2 here, then that determinantal inequality holds for all totally non-negative matrices if and only if whatever word of these row and column operations that we apply gives us a new expression which again is a determinantal inequality for all totally non-negative matrices. So we were basically able to obtain an algorithmic way or algorithmic method to identify whether a smallest multiplicative determinantal inequality holds for all totally non-negative matrices. And the other question was about the existence of the top of the hierarchy. So again, for the smallest multiplicative inequalities of type 1, we were able to show that there is a way to figure out that there do exist certain words of these row and column operations which which when applied on certain complementary determinantal inequalities of the smallest kind yield us a determinantal inequality that was given to us in the beginning. So for the smallest multiplicative inequalities, we were able to test with affirmative result that the answers are true. So to summarize, in this paper, we were able to introduce these index row and column operations, which whenever operate on given determinantal inequality, yield further inequalities overall, which hold for all totally non-negative matrices. And this obviously gives us a way to obtain that there is a certain hierarchy among determinantal inequalities. And because of this hierarchy, we would want to know. A natural question is to know what is at the top of the hierarchy, and we do not know yet what is all at the top of the hierarchy. But clearly, the complementary inequalities are at the top of the hierarchy, and we were able to prove for all the inequalities that we saw so far that the complementary inequalities are in fact those inequalities which sort of generate the rest of the set of inequalities. And the introduction of these row and column operations naturally also give us an algorithmic way to test whether an expression is a determinantal inequality. And we were able to see that trivially for all additive inequalities that we saw today. And we also were able to test the same for the smallest multiplicative inequality. However, that proof required some work. So yeah, so I'll stop here. Thank you for your attention. I'll be happy to take questions.
Let's thank the speaker. And questions? I'll stop the recording and then I guess we can talk freely.